Good morning. All right, so we've got one more example I want to cover in section 4.3, and then we'll get into 4.4. Again, that's what's in the homework that's due for the first part of chapter 4. So we should be able to get through everything we need for that. I'm probably going to push that back one day, just so it's not due by midnight tonight, but you'll have to do it by tomorrow night. That gives you one extra day in case you have any questions or anything. Okay. Again, the plan right now is to try to finish up the rest of this unit by the middle of next week. And so that next test on chapter 4 will be posted most likely on Wednesday of next week, and then due on Friday of next week. Okay, so that's kind of the plan right now. Any questions, comments, concerns before we get started? All right, so let's take a look here at example 10. We want to find the domain for this function. Okay, so if you remember what we've said about logarithms in general, that's right, Alexander. The exam is going to cover everything from the semester. It's not going to be any longer than any test in general, so probably around 10 questions is what I'm looking at, which means that you'd have a couple of questions from each unit. Right, so it's cumulative, it covers everything, but it'll only be at like 2 questions from each unit. Okay, yep. I mean, there will be an exam review, right? So I'm going to post that probably not next week, but the following week is probably when that'll go up. And then that way, if you want to start looking at stuff, or if you want to start studying, right, you can always look at your past test, right? Because that'll give you a good idea of what types of questions could show up on the final too. Okay. All right. So let's take a look at this one. So we've got a natural log of 4 minus x squared. We want to find the domain of this function. So if you remember what we've looked at so far with logarithms in general, what do we know about the domain of a logarithm? So if you just had a basic log, natural log, base 2 log, whatever, what do we know about its domain? Okay, there is an asymptote, right? And where would that asymptote normally be, right, if you didn't have any type of transformation or anything? At 0, right? And then everything on that graph is to which direction of 0? To the right, okay? So everything's greater than 0. So what we're going to say in this case is whatever's inside of your logarithm then, since our domain in general for a logarithm is greater than 0, everything inside this logarithm must be greater than 0. So the way I'm going to find my domain here is I'm going to say that the 4 minus x squared has to be greater than 0. Because we can't do this one based off of transformations, right? Because we have an x squared inside there. So we're just going to have to take everything inside the log and make it greater than 0. Now, how would we solve that inequality? Okay, so we could, right? We could move the 4. What's the other way we could do this one? So look at what we've got on the left-hand side here. It's a difference of squares, right? So how would this factor? Good. 2 minus x and 2 plus x. All right, so I'm going to do it this way just because we are going to have to do a number line and test some points this time because it's a quadratic inequality. And I think having it in this form makes it a little easier to plug those values back in. All right, so now what I'm going to do is I'm going to find the two values here by setting these equal to 0. So 2 minus x equals 0, 2 plus x equals 0. So what are my two x values going to be this time? Okay, good. Plus and minus 2, right? So we get 2 equals x for that one, x equals negative 2 for that one. So again, what we have to do now is generate our number line. Put your two values on there. -2 is the smaller value, 2 is the larger. And now we're going to choose test points in each one of our intervals to figure out where this thing is positive and negative. So what's a test value I could use in that first interval? -3 works, okay? And remember, at this point, we're going to go back and plug it into the original inequality and see if it's positive or negative. Now, it's up to you. We could go to the original and plug it in there. We could plug it into the factored form. Doesn't really matter. I'm going to use the factored form. So 2 minus -3 times 2 plus -3. So 2 minus a -3, is that factor going to be positive or negative? It's going to be positive, right? Because that turns into addition. And then 2 plus -3, is that going to be positive or negative? That one's going to be negative. And what's a positive times a negative going to give us? This is going to be negative overall, right? So this one's equal to a negative. Right, now we need something between the -2 and the 2. So what value could I substitute there? 1 works. Okay, so we'll do 2 minus 1, 2 plus 1. All right, 2 minus 1, positive or negative? That's going to be positive. Good. And 2 plus 1, positive or negative? Positive. Positive times a positive is? That one's going to be positive. Good. So everything in this interval here should be positive. All right, now we need something bigger than 2. So what can we use there? 3 works. And plug that in. We have 2 minus 3, 2 plus 3. 2 minus 3, positive or negative? That's going to be a negative. 2 plus 3 is positive, and a negative times a positive would give us a negative. Everything down here is going to be negative. Right. Any questions up to that point about finding those values, setting up your number line, and figuring out the positives and negatives? All right, now, do we care about positive or negative values this time? Positives, good. So remember, this was a greater than 0, and so we say we are only looking for positive values, so I only care about this interval right here. So what is that interval going to look like then? Perfect, right? So -2 to 2. And in this case, because it's strictly greater than 0, not greater than or equal to, we are not going to include those endpoints. And so our domain for this one is only from -2 to 2, not including -2 and +2. Any questions on that one now? Okay, now I'm going to show you this graph in Desmos just so we can check our answer, right? So you need to know how to do this algebraically, but I am going to switch over to Desmos real quick and graph this because that's a good way to always check and make sure that your domain makes sense. So we graph this one, we've got a natural log, 4 minus x squared. Okay, and we can see in this case that there's actually a vertical asymptote at -2 and a vertical asymptote at +2. And so all of our values for this function now fall between -2 and +2, not including those values, right? Because if I trace, right, you can see that, oops, lost it. Okay, you can see they get closer and closer and closer, but they're never actually going to get to -2. Be careful with tracing though, right? Because eventually you might get to a point where it has to round, and it might actually round up to a -2, or sorry, down to a -2, or up to a +2. So just be careful with that. But in this case, right, it is not including those two values because we need it to be greater than 0. All right. Any questions there now? All right, so that's our last example we're going to do in that section. I'm going to switch over. Four 4.4. All right, so section 4.4, laws of logarithms. So far we've looked at what the functions look like, right? How do we find their domains, that type of thing. Now we're going to look at how do we actually do operations on our logarithms. So we've got 3 basic laws of logarithms that we can use in this case, right? So we're going to let a be a positive number. A can't be equal to 1, just like we talked about before. Now we're going to let these capital letters A, B, and C be any real number. Okay? And A is going to be greater than 0, meaning it's positive. B is also going to be greater than 0, meaning it's positive. That's just so we know that the values inside of our logarithms here are positive, because we know that's the domain of a logarithm. Now, if that's the case, if we have a base A log of A times B, we can actually split that into 2 separate logarithms, keep the base the same, right? They're both base A logs, but now we can do the base A log of A plus the base A log of B. So when you separate multiplication, it actually turns into 2 logarithms with addition in between them. We're also allowed to split up division. So if you have division inside of a logarithm, we can split that into 2 logarithms, again, keeping the bases the same, and then we're going to use subtraction instead. So if you have multiplication and you split it up, it becomes addition. If you have division and you split it up, it becomes subtraction. And our last law of logarithms says that if we have an exponent inside of our logarithm, we can actually bring that to the front and multiply it instead. So we just take that C value, move it out front, and so we end up with C times the base log A. Yes, if the exponent was on the outside of that parentheses, it would still be the same. Okay. Yeah, it's not necessary that it's inside like that. Just be careful to know what the exponent is being applied to, because sometimes you might have multiple operations in there, like multiplication, division, and an exponent. So we just have to be careful with the order that we split things up and where that exponent goes, which log it actually goes with, because sometimes it applies to everything, sometimes it only applies to a single term in there, right? So we just have to be careful with that. Any questions on those laws now? All right, so let's apply them to some actual numbers then. So we've got a base 4 log of 2 plus the base 4 log of 32, and we want to actually evaluate what this is going to give us. So we're actually working with our laws. We're working backwards this time, because notice we've got the addition of 2 logarithms. The first thing I'm going to want to do is actually combine them into a single logarithm. So if I were to do that, since they're both a base 4 log, I'm able to combine them. And what operation would I use to combine them this time? Multiplication. Good. So since we have addition of 2 logs, when I combine them, that becomes multiplication. So we're going to have base 4 log of 2 times 32 now. Again, only combine them if they have the same base, right? But then addition becomes multiplication if we can combine them. Now we simplify what's inside. What's 2 times 32? Good. So we have the base 4 log of 64. And now we just need to evaluate that. Okay, and so we're asking ourselves 4 to what power would give us 64, right? That's what the base 4 log of 64 is. So what would that exponent be? at 4 to the third power, and so this is just going to be 3 then. Because remember, if you remember back to the other section when we were solving these, we had something like this. We would set it equal to x. We would say 4 to the x power equals that, and then we just need to figure out what x is. And in this case, that would have to be a 3, so that's why the value of that logarithm is 3 now. Any questions on how we got that? All right, let's take a look at the next one. Okay, so this time we've got the base 2 log of 80 minus the base 2 log of 5. So again, they're both base 2 logs, so we are able to combine them. What operation are we going to use this time to combine them? Good, this time it becomes division. So we're going to have a base 2 log of 80 divided by 5. Okay, now we simplify what's inside. What is 80 divided by 5? Good, that should give us 16. And so now we just ask ourselves 2 to what power would give us 16? And that should be 4. Perfect. So the base 2 log of 16 is equal to 4. Any questions on that one? And just notice here, right, if we had tried to calculate the base 2 log of 80 or the base 2 log of 5 up front, right, I don't know what 2 to some power is going to give me 5, right? I can't evaluate that logarithm. Same thing with 2 to some power equals 80. I can't figure that out. And so by combining them, though, we actually get something that's much nicer to work with, and we can actually do this one by hand. All right, let's take a look at this last one now. So we got negative 1/3 log of 8. Okay, so what property or law of logarithms could we use this time? Okay, good. We can move that negative 1/3 into the exponent, right? Because if we have a coefficient, we're allowed to move that up. So that's going to give us the log of 8 to the negative 1/3. All right, now let's see if we can simplify that 8 to the negative 1/3. So what can we do with that exponent now? Okay, good. So we can change it to a cube root, and because it's negative, we can also do what with it? What can we do with negative exponents? Move it to the denominator, right? So I'm going to do that step first. So I'm going to write this as 1 over 8 to the positive 1/3. And then we can change that 8 to the 1/3 to a cube root. This just becomes log of 1 over the cube root of 8. Well, what is the cube root of 8? Just 2, right? So now we end up with the log of 1 over 2. Okay, so log of 1/2. Now, what's the base of this logarithm? It's 10, right? So can we raise 10 to some power to give us 1/2? No, right? So there's no good way to do this one. So, but because it's a base 10 log, right? It's a common log. We do have a key on our calculator to get an approximation for this one. So at that point, I would just go to my calculator and I would say, okay, well, what is the decimal approximation for the log of 0.5? And so what does that give us? And we'll go 4 decimal places here. Good. So negative 0.3010. Looks good. Just so you know, right, if you were in WebAssign, right, it would tell you how many decimal places to round to, or if it didn't tell you how many places to round to, then it expects an exact value. And in this case, all you would be able to do for an exact value is stop right there with log of 1/2, because there is no other exact value that you could get for that. You'd have to get a decimal approximation. Any questions on that one now? Sure. So in this case, right, if we have a value, a coefficient out front of a logarithm, one of our laws tells us that we're allowed to move that to the exponent. Okay, so our first step here is to take that negative 1/3 and move it into the exponent inside the log. So that's how we end up with the log of 8 to the negative 1/3. Once we've done that, we know that negative exponents now we can move into the denominator of a fraction to make them positive. So that was the next step here, was to just put this as 1/8 to the positive 1/3 instead, because I know I want a positive exponent. Then remember, fractional exponents can be rewritten as radicals, so I can change that 1/3 power to a cube root instead. So that's how I got the cube root of 8 in my denominator now. And at that point, it's just saying, well, what is the cube root of 8? Well, I know 2 to the 3rd power is 8, so the cube root of 8 should be 2, so that's how I got 1/2. And then at that point, because the base here, right, remember a common log, so log of 1/2 is the same thing as the base 10 log of 1/2. If there is no base, it's an understood 10. There's nothing that I can raise 10 to get 1/2 like I could with the other 2 examples. So at that point, I would just have to put that in the calculator and get that decimal approximation. Okay? Does that help? So anytime it's in front, that's right. Anytime you have a coefficient out front of a logarithm, you can move it into the exponent. Yep. Any other questions on these? All right. So now we want to go the other direction. Okay, so now we've got single logarithms and it's asking us to expand them. So we're going to use those same laws of logarithms. We're going to go the other way though. So if I take a look at this first one here, I have what operation inside first? So if I have 6x, what operation is that? Multiplication. So when I split this into 2 logarithms now, what operation is it going to become? Addition. Good. So I'm going to keep the same base for both. So it's going to be the base 2 log of that first piece, which is 6, plus, and then we need another base 2 log, and then it's just going to be x. Now, always look to see, do I have anything else that I can simplify or expand using my laws of logarithms? In this case, I just have a 6, can't do anything with that. I just have an x, can't do anything with that. That is expanded now. Okay, so we're done with that one. Any questions about how to do that? All right, so let's look at the next one now. We have a base 5 log of x cubed y to the 6th. And so what operation do we have inside here? Okay, good. We have multiplication and we have exponents, right? And so we have laws for both of those things. In this case, we always want to take care of the multiplication piece first, right? Since they have two different exponents, we can't deal with that first, right? Because it's going to be two different things. So split up the multiplication first, then deal with your exponents. So when I do that, like we said before, the multiplication is going to become addition. So we're going to have the base 5 log of x to the third plus the base 5 log of y to the sixth. Any questions about that step? Okay. Now we can use the exponent law, right? So what can we do with our exponents now? Good. Move them to the front. And so for this first one here, that 3 gets moved to the front. So we're going to get 3 times the base 5 log of x. And then our other logarithm, that 6, gets moved to the front. So we end up with 6 times the base 5 log of y. So again, because they were different exponents here, right, the exponents weren't being applied to everything. That's why we had to split up the multiplication first, and then we can just move each of those exponents to the front of their respective logarithms. Okay. Now again, always look inside, make sure there's nothing else you can simplify. In this case, inside my log, I just have an x and a y. No other operations I can simplify there using laws of logarithms, so that's completely expanded now. Any questions on that one? All right, let's take a look at this last one now. So we got natural log of a times b divided by the cube root of c. All right, so what operations do we have in here this time? Okay, good. We've got all three, right? Because we've got the multiplication, we've got the division, and remember we just said that we can change that radical to a fractional exponent, so we've actually got exponents in there too. All right, so the first thing I'm going to do then, I'm going to go ahead and change that cube root to a fractional exponent, and then we'll start to think about what order we need to do things in. So this is going to be the natural log of AB over C to the 1/3 power. So we got multiplication, division, and now we have that exponent also. All right, so we want to make sure that whatever we do, it's going to actually combine back to give us what we started with. So just think about order of operations as you're doing this, just to make sure it's going to work out. I've got my multiplication in the numerator. That's the first thing I'm going to want to be able to combine when I do this. So that's the first thing I'm going to separate now. So if I separate that, what's that going to look like? Okay, good. Just natural log of A plus the natural log of B. Because if we combine that, that would give us that multiplication of A times B inside the natural log. Then what are we going to do with that C to the 1/3 in the denominator? Good. It's going to become minus. And for right now, I'm just going to put the natural log of C to the 1/3 power. So now I've got my addition, my subtraction, right? Because that way I end up with A times B and then divided by C to the 1/3. Now, when we look at everything inside here, right, I have an A, can't do anything with that. I have a B, I can't do anything with that. But what can we do with that C to the 1/3 now? Now we can move the exponent, right? So I'm going to bring that exponent out front. That's going to give us a minus 1/3 natural log of C. And at that point, we only have a C inside that logarithm. that is now completely expanded. We can't do anything else with it. Now, if we were working backwards here, right, always take care of your exponents first. So you'd want to move the exponent up first, then you can take care of your multiplication and division at that point if you were trying to recombine these, okay? In this case, we don't really need any parentheses. And the reason is if I were to go from left to right, I would say A times B and then divided by C to the 1/3. And so all of this would give us what we started with. If you ever have a case where, let's say you have multiplication in the denominator and you need that stuff grouped together, then yes, you might end up with parentheses. Okay, but for this one in particular, we don't need it because just going from left to right is going to give us what we started with anyway. Okay. Yeah, especially when you have division with multiplication in the denominator, a lot of those cases you will end up with that parentheses around all the stuff that comes out of the denominator. Any other questions here? All right. So now we're going to combine each one of these into a single logarithm. And so again, we have to think through what are the steps, what would we do first, right, so that we can get all this together. So what do you think we should do first with these if I want to combine them? Okay, good. So we need to move the exponent first, all right? So the 1/2 for sure, right? We can move that into our exponent. And notice here there's parentheses of x plus 1 inside the log. So that 1/2 gets applied to the entire set of parentheses. Is there any other exponent we can move? The 3 also, right? So this 3 is also going to move into our exponent. So we're going to end up with the log of x to the 3rd plus the log of x plus 1 to the 1/2. So always deal with those exponents first. So if you've got coefficients, move those into the exponent before you try any multiplication or division. Now that we've done that, they're both common logs, right? Both base 10 logs. Now we can combine those. What operation are we going to use to combine them this time? Multiplication, good. So we're going to get a single log, and then it's going to be x cubed times x plus 1 to the 1/2. And that's it, right? That's all we have to do there. We've combined them into a single logarithm. We did our steps correctly, so this would actually expand back out into what we started with. And so that is our final answer. Now, don't try to distribute anything inside there, right? Because that x plus 1 is being raised to the 1/2 power. That's like a square root. Therefore, we can't distribute that x cubed into that set of parentheses there. Any questions on that one? All right, let's look at the second one. So what's the first thing we're going to want to do? Okay, good. Move your exponents first, right? So I've got this 3, move that into my exponent here. I've got this 1/2, and I can go to the exponent there. And then I've got this 4 that can go to the exponent there. And notice I'm not thinking of that as a -4, right? Because the minus piece is going to be taken care of when we combine them. So it's only the 4 that's going to get moved. So we're going to get natural log of s to the 3rd plus natural log of t to the 1/2 minus natural log t squared plus 1 to the 4th. All right, now that we've got that, what can we do next? Okay, good. So we have both multiplication and division this time. And again, reading from left to right, since I don't have any grouping symbols, right, I'm just going to go from left to right this time. I'm going to multiply the s cubed and the t to the 1/2, and then I'm going to divide by the t squared plus 1 to the 4th. So this becomes natural log of s cubed t to the 1/2 all over t squared plus 1 raised to the 4th power. Okay, so this would be our final answer here, the natural log of all of that stuff there. Any questions on that one? All right. All right, so now the law of forgetting. Okay, so if a task is learned at a performance level P sub 0, so that's basically what did we know the first, like when we first learned it, our initial learning, then after a time interval T, the performance level P is going to satisfy this equation. All right, so the first thing we're asked to do here is solve that equation for P, and then once we know that, then we'll use that to answer the question at the bottom here. Okay, so we're going to use those laws of logarithms here, see if we can combine some stuff so that we can try to get P by itself this time. So let's look at the right-hand side here. What's one thing I could do if I wanted to try to combine these? Yeah, I can move the C into the exponent, right? Because we have this coefficient here that can be an exponent. That'll give us the log of P equals log of P sub 0 minus the log of T plus 1 to the C power. Now I have common logs everywhere here, right? So on the right-hand side, if I combine those two logarithms, what operation would I need to use there? Division, right? Because that subtraction will become division. So now we end up with the log of P equals log of, and now in here we're just going to have P sub 0 divided by T plus 1 raised to the C power. Any questions up to that point? So just applying those laws of logarithms so we can get all of those combined into a single log on the right-hand side. All right, now here's what we have to look at. We've got log of P equals log of P sub 0 divided by T plus 1 raised to the C power. I want to solve for P. All right, so I want to know what P is equal to. What do you think we could do at this point? Okay, so when you say just plug in, what do you mean by that? All right, so I'm not looking at the question at the bottom yet, right? I'm still trying to do this piece because I still don't know what just P is equal to. I know what log of P is equal to, right? But I just want P. So what would I do next? Okay. So that's one option, right? We could try to rewrite this thing in exponential form. It's actually easier than that, though. So if we think about this, right, we've got a base 10 log of p on the left. We've got a base 10 log of p sub 0 over t plus 1 to the c on the right. Well, if they're equal to each other, then that means the stuff inside the logs would have to be equal, right? So if I've got a base 10 log equal to a base 10 log, the stuff inside the one on the left has to be equal to the stuff inside on the right. So all I really have to do in this case is drop the logarithms and set the stuff inside equal to each other. And so I'm just going to end up with p equals p sub 0 divided by, sorry, I'm squeezing this in here, t plus 1 to the c power. And that'll always be the case. If you have the same type of log on both sides of an equation like that, then you can just drop the logarithms and just set the stuff inside equal, because that stuff has to be equal if those logarithms are equal now. Okay? As long as the bases are the same. Any questions on that? All right, so that's the first part, right? We solve for P. Now let's look at the question. It says, if your score on a history test is 90, what score would you expect to get on a similar test after 2 months? And then we'll do after a year. So we'll do 2 months first. And we're assuming here that our C value is 0.2, right? So they're giving us that constant in terms of like how much we're going to forget, basically, after 2 months. And so all we have to do now is plug in, right? Like you were saying, Destry. So I'm looking for what my score would be. So that's our P. What's our P sub 0 going to be this time? The 90, right? Because that's what we scored initially. Right? Then in the denominator, we're going to have T plus 1. So what's our T value this time? It's going to be 2, right? And it doesn't really tell us that T is measured in months, but in this case it is. So we're going to have 2 plus 1. And then our C value is given right here. And so we're just going to put 0.2 in our exponent. Now we just need to simplify all of that. And so if we do 90 divided by, in this case, that'd be 3 to the 0.2. What should we get there? All right, good. And I'm just going to round this to the nearest whole number, right? Since we're talking about a test score, right? That's normally what we would do. So I'm just going to say 72. And so basically what this tells us is if we initially made a 90 on a history test and we waited 2 months, right, we're naturally going to forget some things, and we could expect after 2 months that we'd probably get about a 72 on that test, okay, according to this model, right? Any questions on that one? Okay, now they also want to know after a year, right? So we're going to do the same thing here. P equals our initial test score is still the same. That's still a 90. What's our T value going to be this time? 12. Good, because we're talking about months. So a year will be 12 months. And our C value is still the same, 0.2. So this time we're actually doing 90 divided by 13 to the 0.2. Let's see what you get for that one. Yeah, so if we round that one off, it'll be a 54. Okay, so again, what that says is if we were to take a test and get a 90, wait about a year and try to take that test again, just according to how much we're going to forget, you're probably going to make about a 54 the second time you take it. Okay. And again, this model is probably assuming, right, that you're not studying along the way, or it's not like you're taking a final exam a year later and you've actually been reviewing the material. This is like, cold turkey. You go in and try to take the same test without actually looking at the material again. That's how much you would probably forget. Okay. Any questions on that one? All right. Change of base. Okay. So a lot of calculators now will allow you to actually go in and put a different base in there, right? So if you have like a TI-84 Plus or newer with upgraded firmware, you can probably do that anyway. But if you don't, right, and so this is mostly for like older calculators, we actually have the change of base formula that allows us to put things into the calculator that we otherwise wouldn't have been able to. So what we're going to do now is we're going to take the log of whatever's inside over the log of whatever the base is. Okay, and this new base, the A, can be anything we want it to. So the reason this is useful is that I can actually change this to something like log of X over log of B, where I use common logarithms. Well, common logarithms are definitely on your calculator. Or I could write this as natural log of X over natural log of B. Because again, we have a natural log key on our calculator. So now any type of logarithm that we have, no matter what the base is, we could rewrite it in a form that we could put into the calculator. Okay, so that's what change of base is for. But again, a lot of newer calculators, you can actually type in a base 2 log of whatever or a base 5 log of whatever. Right? So if you're able to do that, then this isn't as necessary. But if you don't have that feature on your calculator, now you have a way that you can actually type these in. Okay. So let's see if we can do this with just a couple of them. So if I want to use change of base here for base 8 log of 5, okay, and I want to use either common logs or natural logs, it doesn't matter, just something that I know I can put in the calculator. How could I rewrite that first one? All right, so log 8 over log 5. So be careful here, right? It's always the log of whatever's inside over the log of whatever the base is, right? So we just need to switch that. So we're going to do the log of 5 divided by the log of 8 instead. Okay? Right, but now we have a common log of 5 divided by a common log of 8. That we should be able to put into our calculator. It says here we want 5 decimal places. Okay, so now let's put that in the calculator. And so what do we get to 5 decimal places? So just for the sake of time here, because we're only got like a minute left, I'm going to say this is 0.77398 if we put that into the calculator. Now, like I said, it doesn't matter what you change your base to. So if I want to use natural logs instead, I could do natural log of 5 divided by natural log of 8. And you'll see that if you put natural log of 5 divided by natural log of 8 into your calculator, it's going to give you exactly that same decimal. Okay, so that's why, change a base, we can change it to any base we want. And that's why I said it doesn't matter if you use common logs or natural logs, it's still equivalent either way. Okay. So we are at time there. Yeah, and if your calculator does the, whatever base you want, then you can put in just like that, base 8 log of 5, and it should give you that same decimal, right? If you don't have a calculator that will allow you to put in those bases, then you're going to have to use change to use either common logs or natural logs. Okay. It's always the value here that goes in your numerator and always the base that goes in your denominator. Okay. All right. Yeah, and so if you need to get to that, Alexander's got the steps there on the 84. You go to the alpha window and then 5. It should give you that change of base. Okay. All right, so we'll stop there for today. That's all we've got for section 4. I am going to push the homework back one day, so it'll be due by tomorrow night at midnight. Let me know if you've got any questions on that. Send me those questions in WebAssign. Come see me during student hours tomorrow if you need to. Otherwise, have a great day, and I will see you all tomorrow.